This is going to be, I hope, an interesting talk. I've never done anything quite like this before. And at some points, it may seem like it's going to be a hodgepodge of topics, but I assure you there's a payoff at the end. I do need to tell you that this is going to run a little bit longer than your typical talk. And to keep it manageable, I'm going to ask that you hold questions until the end, until we see how much time we have left. I know some of you need to leave to catch trains, for example. If you need to leave, please, I won't be offended. I'll be offended if you leave in 5 minutes, but you know, that's a different story. So let's get this underway. Before we get technical, I'd like to acknowledge a whole lot of people, and I actually don't have room for all of the names. Some of these people were my teachers. Some of these people are my colleagues on the C++ Standards Committee. Some of these people have spoken and have left an impression on me, but they've all contributed something. They've inspired and they've informed, and I am grateful. In particular, this gentleman wrote something very influential, at least to me, because we're all here to improve our understanding. And with this in mind, everything I'm going to talk about tonight is probably stuff you already know, but perhaps not in depth, because you can't tell a beginner everything you know. In fact, that's a bad thing to do. So my intent is not to tell you something you already know. Please don't be offended, but to explore in a little bit more depth. So this talk is going to be in 3 parts. I want to explore what I've called a targeted selection of features. And I want to do these in more than what I call the surface behaviors that we teach novices, for example. And as we go through these things, please look for commonalities, look for insights that'll help us all reason more effectively about our programs. Because in the final analysis, reasoning is one of our principal tools in programming. Once I'm done with that, and that'll be the majority of this evening's talk, I'm going to break off to explore a problem. It's not going to seem like it's connected to anything, but it will. This problem affects a number of algorithms, both in the standard and other algorithms as well. And we want to look at what the issues are. And then in part 3, I want to connect parts 1 and 2. All right, so in a sense, this talk is Y-shaped. A little bit here, a lot down there at the end, okay? So we're going to apply the features from part 1 in some interesting ways. Going to solve the issues brought up in part 2. And best of all, the code that results is going to be remarkably short. Okay. Part 1. I'm going to start with value categories. We've all heard of value categories, but it's been my experience that many C++ programmers, although know about value categories, don't appreciate how deeply they pervade the C++ language and library. So a little bit of history. L values and R values have been around for 40+ years now. But ever since C++ 11, we've had some refinements of those categories. We now have GL values, we have PR values, and we have X values. And this is a quote from the standard. When I quote the standard, I'll give you the citation somewhere in the corner or afterwards in case you want to explore a little further. What I've discovered a lot of programmers don't appreciate is that despite the name, which includes the term value, these terms don't apply to values. They apply to expressions. So we can talk about a PR value expression, for example. And every expression belongs to exactly one of these three: L value, X value, or PR value, and that's what we term the value category. Every C++ operator, if you look at the standard, every operator specifies two things: the value category required of each operand and the value category promised for the result of the operator when it's applied. Okay? So there's no operator that you can write, there's no expression that you can write that does not have a predetermined value category as its result and predetermined value category requirements of the operands. And there's a taxonomy, there's a hierarchy here. And you may have seen this diagram or some version of it before, but here's how they relate. And at first glance, this looks asymmetrical. You'd think L value and R value should be at the same level, but they're not, and it's for historical reasons. If we had changed where we put L values, all previous programs would just suddenly break in some mysterious ways, or potentially so. And C++, as we evolve the language, we're big on maintaining backwards compatibility. Now, what a lot of programmers don't appreciate is that this has an influence on the decal type operator. The decal type of an L value expression is always an L value reference type. And you'll see me abbreviate that LREF from time to time. An X value expression, its decal type, always has an R value reference type, and a PR value expression is always a non-reference type. And this is what I like to call the type encoded value category. Right? It's an encoding of the value category in the type of the result, for example. Okay? Now let me give you an example, because decal type is in some sense a little bit schizophrenic. The standard says that the type and value category of a parenthesized expression is the same as what you get to the unparenthesized expression. So parentheses do not affect the value category, except, okay? Here's what the difference is. An expression is treated differently by decal type than the way decal type treats an unparenthesized ID expression, which we can think of as just a name. But C++ has funny looking names, right? We overloaded operator functions have funny looking names, operator plus. Template specializations have funny looking names, template IDs with angle brackets and so on. Those are all ID expressions of various kinds. So look at this little piece of code. And I assure you that these static asserts will not fire. They will pass. And I want to be sure we get a really good handle on how this works and why it works the way it does. So let's first take a look at line that I've numbered 1. Okay? Decal type of the variable k is going to report int. Why? Well, because k is declared to be int. Done. That's an unparenthesized ID expression. Look what happens when I parenthesize it. Suddenly it's int const ref. Why? Well, int because k is declared int. Const because we're inside a const qualified function, member function. And ref because it's still an L value expression. And that's the type encoding. Okay? So please remember those encodings, at least for the rest of the evening. There's not going to be a quiz at the end. You don't have to worry. As a reminder, if you have an expression, if it's an L value expression, then decal type will be an L value reference. If it's an X value, you get an R value reference. If it's a PR value expression, you get a non-reference. Okay? What's interesting about this little table is that you can switch the when and the then. It goes the other way too. If decal type reports tref, you started with an L value expression and so forth. Okay? I haven't seen anybody present that before. Here's something else that I've discovered isn't always well understood. C++ expressions never, by themselves, have a reference type. When I first learned this, my jaw dropped. Now, it's been 20 years ago and it's, rehinged itself by now, but still. Okay, there are no expressions of any reference type. And there's the citation from the standard. It's one little line in the standard, and it's buried as hip deep in the middle of other stuff. Okay? If it starts out having a reference type, that reference is dropped prior to further analysis, as it says. Okay? And that's useful to know. And in case you want to confirm your understanding, let me show you a little bit of code that you can use to double check yourself, if you so choose. I'm going to define a template, first a primary. It's just a pointer, value category. I've abbreviated, but you get the idea. It has that string literal. And I have two specializations for the other two value categories that we care about. And once you have that, you can display the value category for any expression of your choice. Okay? For example, you could do it like that. Just plug in whatever expression you want where I've written the E. Okay? And if you don't like cout, use print line or, whatever your favorite display is. Okay? And here are two concrete examples that I've discovered are also not particularly well understood. The value category of a pre-increment expression is an L value. The value category of a post-increment expression is a PR value. And if anybody ever tells you that pre and post increment are equivalent, phooey on them. They're not. They've never been. It's always been this or the equivalent. Okay? They're not interchangeable. And I can't tell you how many arguments I've had with seasoned programmers who don't believe me. There is a copy when you use a post increment. Try to write the function yourself. You can't do it without a copy. You got to return the original value after it's been changed. You have to have a copy. It's true, some compilers can optimize that out with certain settings. But remember, okay. All right. So while we're talking about decal type, I want to talk a little bit about decal type auto. So let's start with just these two declarations and we'll refer to them for the rest of the page. Here's a pair of direct initializations. And they seem to give the same result. And that's correct. And if I do a copy initialization instead of direct initialization, I still get the same result. Yeah, that's an unparenthesized initializer, right? Watch what happens. As soon as you turn it into an expression, the decal type semantics kick in. See what I mean? It's an L value expression, so you get an L value reference. And if you do copy initialization and you start with an X value expression, and there are more details, but not yet, you get these results. Okay? So auto and decal type auto aren't interchangeable either. Here's a little bit more about that. We'll keep the same declaration as before. Here's what happens with braced initializers. Well, braced initializer is not an expression, so decal type auto just doesn't work. Decal type doesn't handle this case. If you decorate, for example, with a star, a pointer, Works fine for auto, must not do that for decal type auto. No decorations. Decal type does the whole business. Doesn't need help from you. And what happens when you try to deduce a return type? Decal type of parenthesized X? Well, we know what to expect. You get an L value reference. It's an L value expression. But when you say decal type auto, it goes and looks at the operand of the return. And of course, if you have multiple returns, they better be consistent, right? Okay, well, there are special rules about return statements, and they have changed over time. What I'm showing you is the latest and presumably greatest. But if you happen to be dealing with code bases from C++ 11 or 14 or 17, these might not quite be the same rules. They have changed. Okay? Return statements are special because we want to enable move semantics as much as we can. So we've done more and more of that over time. Okay. Change of topic. Qualifier unification. You're not going to find that term anywhere else. We all know this. If you apply a reference qualifier to a type, of course you get a reference qualified type. Nothing new there. And here are two quick examples. No big deal. Everybody knows this. But what happens if you start with a type that's already reference qualified? For example, if I have an alias like R up here, what does it mean to say rref or rrefref? Well, language, as we know, has no such thing as a reference to a reference type. Doesn't exist. So what happens is that the two references, the existing one and the one you're trying to apply, they get combined. And the word that standard uses is collapse. Okay? And how does that happen? Well, this is my, 5-word explanation. If you either start with an L value reference or you're trying to apply an L value reference, you're going to end with an L value reference. Okay? So rref is the same as intref ref, but that collapses and you end up with intref, which is the same as the R you started with, of course. Okay? If I do rrefref, it still collapses and the L value reference wins. Here's a little table. Okay? If that's reminiscent of Boolean and or Boolean or, you're right. Okay? The only way you get an R value reference is if you start with one and apply one. Okay? Otherwise, the L value reference wins. But there are other kinds of qualifiers. They have CV qualifiers, const volatile, right? I have to admit, I very rarely needed to use volatile, but that's just me. When we combine those, when we unify those, we describe it as a union rather than a collapse. So if I start with this alias and I want to const qualify C, I still end up with int const, which is the same as what I started with. And you can verify all this with an appropriate static assert, right? Now, what happens if you start with a type that has both kinds of qualifiers? For example, that. Well, you can't CV qualify a reference type in C++. There's no such thing. I mean, in some sense, every reference is const qualified implicitly, right? You can't reseat a reference. You can't change it once it refers to something. It's always going to refer to that same thing, okay? So what happens is that any extra CV qualifiers are simply ignored, but any reference qualifiers you want to apply will collapse as usual. Okay, for example, like this. Or this. Okay? The L value reference will always win if it's present. Okay, moving on. We have some type traits in the standard library that do some of this for us. They're named add for some bizarre reason. There's no addition involved, right? We're trying to apply qualifiers. But certain types need special handling because of the rules in the core language. So very simply, here are the traits that add reference qualifiers. We have add L value reference, but you can't put a reference on a void. There's no such thing. There's no reference to void type, right? So this trait doesn't do that. Okay, you start with void, you end with void. Similarly, for adding R value reference types, but there's an additional gotcha. There is no such thing as an R value reference to a function type. Does not exist. So you can add an R value reference and you're going to get an L value reference. Okay? Even if you started with a non-reference type. And then we have three traits that add CV qualifiers. Add const. Well, as we've already said, you can't CV qualify function or reference types. So this doesn't. And the same restriction for add volatile and add CV. Okay? It always pays to know the type system. Always. Okay? One of the very first things I tell people when I give my template programming course. Need to know the type system well. C++ is famous for its type system. Now here's something I haven't seen anywhere else. We're going to do all of this stuff backwards. Here's a simple example to show you what I'm talking about. Line 1. I write a declaration of a variable x and to give it type t. And my intention is when I'm done, if I say decl type x, I want the result to be int. So what does t have to be? Somewhere up above, I must have said using t equals int, right? Or maybe there's a type, same thing, right? Type def. See how this works? Now let's make it interesting. I want decl type of x to be an int const. Now I can write my declaration in two different ways, lines 2 and 3, right? If I write simply tx, then t had better be an int const. But if I write t const, as in line 3, it suffices for t to be an int. Keep that in mind, please. It suffices. It's enough. Because I could say int const, but then it's just going to do the union, right? So it's not necessary. What about a reference? I want decl type of x to be a reference to an int. And I have three choices in how I declare x, lines 4, 5, and 6. If I write it as in line 4, then t had better be an int ref to get what I want. If I write it as in line 5, then it suffices for t to be an int. And if I write it as line 6, then t again has to be an int ref. And reference collapsing rules will do what I want. See how this works? It's backwards. I'm starting with a potentially collapsed type and working backwards. And finally, lines 7 and 8. I want an int ref, and I have only two choices, lines 7 and 8. And you see what t has to be in each case. I'll leave that up there for a few seconds while you think about. But there's a moral to this story. What we've just done is type deduction. I just didn't use the name until now. And the takeaway is that we're deducing t starting from decl type of x. I know what I want the result to be, and I'm working my way backwards. Please keep this in mind. Okay, change of topic. If you're going to write an overload set of a function that takes a parameter by reference, you have four choices. These are your four choices in how you declare the parameter. Prior to C++11, you only had the two choices in the left blue box. Since C++11, you now additionally have the two choices in the right blue box. So imagine those are your parameter types. Now let's think about arguments. The arguments arguments are always treated as expressions, right? So I could have arguments that are mutable L values or mutable R values, or I can have arguments that are immutable L or R values. Those are the four possibilities. So how does the binding work? Well, let's look at mutable L value. If I have both overloads, we prefer tref. If that one isn't available, it'll fall back to tconstref. Nothing new. It's been this way since C++98. And if I have a const L value, well, then I have exactly one choice. Okay? Again, this has been this way essentially forever. Since C++11, we also have additional choices to handle R values. And when I say R values, I mean both PR values and X values, right? They're treated the same for all intents and purposes in this context. So if I have a const R value, it binds one way to prefer. It prefers the R value constref. If that's not available, it falls back to the other. And if I have a mutable R value, there are actually three choices. And I've numbered them. Number one is always preferred. If that's not available, number two. And if that's not available, then falls back to number three. Okay? And it's been this way ever since C++11. A couple of interesting things to note about this diagram. tconstref is available for all arguments. So some people have dubbed it the universal receiver or the universal parameter type. You can always bind there. And the other item to notice, tref is what enables move semantics. Now, I'm not going to go into move semantics tonight, although I've got a couple of interesting slides, but we're short on time. So now I want to bring a couple things together. Categories influence type deduction. As most of you I'm sure are aware, if you write ref and apply it to a type that's going to be deduced, for example, tref, in exactly that form, what you have is termed a forwarding reference. Okay? Scott Myers started out calling it a universal reference. Some people still prefer that, but that's not what the standard said. Excuse me. A couple of quick examples. If you say auto ref, that's a forwarding reference. And what you get is decal type of T, but there's no other name for it. You can get the type by saying decal type T, but it's anonymous. There's no name there for the type, right? Here's the gotcha. The same thing is true in this context. There's the forwarding reference and the parameter. The type of variable little t is still decal type of T, but there is no name for that type. There isn't. Now, people who haven't dealt with this before will say, oh, no, 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 it's type T. That's my name for it. No, it's not. Well, it sometimes is, which means it's not. Okay. Type deduction works off some initializer. Why am I talking about initializer? Well, because parameter passage is initialization. Standard says so. So's return. Those are initializations, right? We have an initialization, there's an initializer. The forwarding reference doesn't only look at the type, it actually looks at the value category. So decal type of little t is always going to be some reference type. Either because I passed in an L value expression, or I passed in an R value expression, and somebody's always mentally thinking, wait, if it's an R value, if it's, there's not always a ref there. There's one case where there's a non-ref. But it says tref right there in the parameter. So there's always a reference. So it's either decal type of little t is either an L value reference or it's an R value reference type, always. And from that, by working backwards, you can figure out what t is. And as we saw, it doesn't always match. Okay, it matches sometimes, but not always. So let's look at a specific example. I'm going to call g of x, and here's g. Look at that expression at the end there. Decal type of x ref. And if decal type of x is an L value reference type, then reference collapsing fits in here, right? Okay. So case one, suppose I have declared x as an int and I give it some initial value. I don't really care what it is. So when I call, x is going to be an L value expression. So in the call g of x, decal type of x will be int ref because it's an L value expression. And so will be decal type of t. And since tref now denotes that int ref, t must denote int ref, as we just saw by doing our backwards reference collapsing. Case two. Let's define x this way. Initializer is going to be a PR value expression. Okay? So when I call g of x, decal type of x is just going to be int. Decal type of t will be int ref. There's a ref up there. Okay. And since that t ref now means int ref, it suffices for t to denote int, which is not the same as decal type of little t. Okay. All right. Everybody see how it works? Okay. Change of topic. Static cast. We know this. This is how static cast works. It's a conversion, right? Well, no, not always. Okay. But the standard says if your t is already an L value reference type, the result will be the result of the cast, right? That's an operator. Every operator has a value category promised as its result type, remember? So the result was going to be an L value. If you start with an R value reference type, the result of the cast will be an R X value expression, because you can work it backwards. Remember my arrow? Otherwise, you get a PR value. Direct quote from the standard. By the way, Please note this similarity. A function call expression, the function call expression, we're not talking about parameter passage now. We're talking the expression like f of x or g of x. If the result type is an L-value reference type, the expression will be an L-value expression. And so on, and so on. Now, I want to zero in on a particular kind of static cast. One that looks exactly like that for some type t and some variable x, some expression x. And of course, reference collapsing might apply, depends on what t is, right? Suppose x is a variable, maybe a function parameter, of some type t, possibly deduced. And there are three possibilities, right? If t is an L-value reference type, the result of the cast will be an L-value expression. If it's an R, you get the idea. You see the pattern? It's all over the place. It's everywhere. So what's interesting about this particular set of rules is that this particular expression is in effect doing the same kind of encoding that decal type does, encoding the value category in the resulting type. We get both the type and the value category of the argument. This is important. And I'm about to tell you why. I'd like you to look at these two function templates. It looks like I've got them out of order, but I wanted to be sure that Calc 1 can call Calc 2. Okay? All right. Is that an okay thing to do? Well, of course it is. And we use the term forwarding here. All right? I've called Calc 1. Somebody's called Calc 1. Calc 1 has a parameter t, little t, and then it uses that as its argument to Calc 2. So it's forwarding that little t. But there's a problem here. The problem is that t's type in Calc 1 might not be the same type as u's type in Calc 2. Why not? Because little t in this context, in the call, is an L-value expression, which means decal type of u will always be an L-value reference type, no matter what t's was. Now remember, that little t started out somewhere else. We called Calc 1. And so the vocabulary that's been adopted is to say that this is imperfect forwarding, because we've messed up the value category. So if we want perfect forwarding, and believe me, we do, we have to preserve not only the type, but also the value category. And this is how that happens. This particular cast that I just talked about on the previous page is how we do that. Remember, that particular cast preserves an encoded value category. And the more common way of expressing this is by calling standard forward. And a lot of people define this is so common if you do a lot of generic programming. This is so common, people define a macro usually named FWD to mean the same thing. Okay? And what that does, as we've seen, is it maps L-value expressions to L-value reference types and R-value expressions to R-value reference types. Change of topic. The ternary, and I know a lot of people don't like the ternary, too damn bad. It's part of the language. It doesn't replace anything else. Here's a question for you. Just answer it inside your head. 2 lines of code. Do they have identical semantics? Hint, no. Looks like they do. And they do if X and Y have the same type. In fact, if they have different types, these are potentially ill-formed, depending on the specific types. The way the ternary operator works is that it looks for something that's often called a target type. For example, well, and it takes into account both types and value categories. If you have, let's say, X is an int and Y is a float, then the target type is going to be float. And if you have one an int and the other one's an unsigned, the target type is going to be an unsigned, which is too bad, but that's the rules. Another example. If I have two types, struct A and struct B, that inherits from A, the target type of those two expressions is going to be A. And if I alias C and make it mean B const, then the target type of A and C is going to be A const. Okay? I don't think I've ever seen this explained in any freshman course. Okay, so what's the big deal about value categories? Well, I'll explain. Just assume I have these four declarations. Okay? One variable, three functions, different return types on the functions. Here's a table. And this is going to be commutative. Doesn't matter whether this is the second or the third operand, all right, they work the same way. It's going to look at both types, both value categories. If one of the operands is a plain old variable k, then what you get depends on the value category of the other operand. You're going to get an int ref if you have two L value expressions, and you're going to get a plain int if one of them is an R value, specifically a PR value. That's important. Some more cases. If I start with a different L value expression, and that's an L value expression, right? It returns a reference. Sorry, what am I saying? Got it backwards. X does not return a reference. X returns an int, so that's a PR value expression. All three of those give me an int as a result. And the result is a PR value expression. Remember, there's a promised value category for the result. Okay? Two more. Now I have an L value expression calling L. There are only two cases I have not yet considered. If I have two L value expressions, I get an L value expression. That's a reference type. Otherwise, I get an int, and that's a PR value expression then. And I'm talking about the whole ternary operator ends up giving you a PR value. And finally, both operands are X value expressions. And now I get an int ref. And the result is an X value expression. This is going to turn out to be problematical because of that last line. But this is how it works. All right, change of topic. The standard library talks about partially ordered types. We say that a type is partially ordered if those four expressions are well formed for variables of that type, and you get a bool as a result, or something that you can convert to a bool. That's what it means to be partially ordered for some type. Okay. There's also the notion of partially ordered with. I don't know why we have phrases that end with prepositions, but we do. Okay. And this applies when you have distinct types for the two operands. Okay. We say the one type is partially ordered with the other type if the same expressions are well formed when you have one from column A and one from column B, right? And the result gives you bool, or boolish, I've called it. Okay. And we sometimes say that these kinds of expressions are cross-type. Different programming languages have different vocabulary for this, but these are sometimes known as cross-type expressions. And we can extend, and this is common, we can extend these definitions for reference types. All you have to do is apply the trait remove reference, and you're back to where you started from. Okay. Now, this trips up almost every novice programmer I've ever met. Simple expression -1 less than 1u. This is death. Okay? Mathematically true, C++ false. Kills me every time I have to teach this. Why? Operands are of different types. No comparison between different types. Does not exist. So one gets converted to the other. We have the target type. We've heard this before, right? And when you have an int and an unsigned, that target type is unsigned. And unfortunately, small ints that are negative convert to very large unsigned. Why did they do it this way? Well, it's been this way for, well, ever since C, actually, right? So 50-ish years. And my theory, I don't know this for a fact, my theory is because it's cheap. No bits have to change, just their interpretation, right? But, and this is still relatively new, there's now an algorithm in the standard library named CMP-less, which I pronounce compare less, but other people have other acronyms for CMP. Something multi-programming, multi-processing, cooperative multi-programming, yeah, sure. And that does the right thing. So please, God, compare things of equal types. And if you absolutely positively can't, better have a damn good reason, and B, call this algorithm and get the right answer, please. No pun intended. Yeah, I know. I'm old. I'm not stupid. Okay. And what if you have floating point values involved? For example, comparing floats with ints or with other floats in the presence of possible nans. Well, there's an algorithm for that. It's named isLess. You hand it values of arithmetic types. So either ints or floats. And it's supposed to do the right thing with nans. Still tricky, but does at least something reasonable. Okay. And now that we know about all of that stuff and the potential pitfalls, typically we want to do this to figure out something about the order of a pair of values. So if you have a partially ordered type, it means I can apply less than, right? Almost every novice I've ever met falls into this pitfall. To answer the question, I hand you A and then I hand you B, are they in order? The reflex is, okay, A less than B. And I'm sorry, that's right only some of the time. If the answer is true, you're right, it works. If the answer is false, it doesn't work. They might be in order even when the answer is false because they might be equal. And if they're equal, you can't say that they're out of order. So they must be in order, right? Okay. In my experience, it's more useful most of the time to ask whether the values are out of order rather than ask whether they're in order. And I typically do it this way. I have something named simply less, and it does the right thing, okay? The reason that I think it's most useful is when you get a true answer from this function, then I usually have extra work to do or different work to do or something that's not the default, right? I mean, think about it. If you're sorting, if they're already in order, you don't have anything to do. So when the answer is false, you can usually return early, for example. Okay? Or often, perhaps. Okay. No, not yet. Okay. Another topic. Told you, doesn't this seem like a hodgepodge? The polite word is potpourri. Okay. Standard says that a simple type specifier followed by a parenthesized optional expression list or by a, you can read it yourself. Here's the key. It constructs a value of the specified type from that initializer, right? Okay. So I assume I have some expression such that its decal type is trefref. I know this is not full generality. I'm honing in on something very specific. I've got something in mind, okay? So there are two cases that are of special interest today. If T is just a simple type, then decal type of E being trefref means that E must have been an R-value expression. So I get something of type T by calling a constructor of T. Might be a copy constructor, might be a move constructor, etc. Okay? Case two. If T is an L reference type, then decal type of E is an L reference, L value. So we started with an L value expression, reference collapsing and all that. So T of E has absolutely no effect. You have an L value reference type, you're trying to cast it to an L value reference type. That's a no-op. Okay, doesn't do anything. No penalty. Just looks impressive. Okay. Talk about function return. Statement of the form return E for some expression E. We know this. Evaluates E, terminates the function, hands back E's result. And there might be an implicit conversion there. Depends on the return type of the function, right? Okay. There are two cases we want to talk about today. Starting to sound familiar? If E is an, sorry, the rules have changed, okay? This may not apply if you're still at 14 or 17 or 11, okay? The rules have changed. If you have an identifier expression that names a local variable, it is treated as an X value. Treated as an X value. Okay? And the reason for that is to allow the possibility of calling a move constructor or a fallback to a copy constructor, for example, okay, to get your result. But if E is a PR value expression, then you might get copy elision. And you get direct initialization. So no constructor is actually been called when the types match, of course. Everybody take a breath. Thus endeth part one. Okay? The hodgepodge, oh, sorry, the potpourri is finished. Okay. So part two, total shift of topic. Total shift. So what's wrong? Why am I bringing you down this garden path? I'm going to start with Min as my poster child. Okay, I'll have another poster child in a little bit. I'm going to start with Min. So here's a simple and correct implementation, but this is not conforming to the standard because the standard library specifies passing by reference, both the call and the return. Okay? So this is a correct implementation according to the standard spec. Okay. Now, why the by reference? Well, it mitigates potentially expensive copying. For example, if you had long strings, then copies would be expensive. And so there's a modest improvement to be had here. Okay, fine. But the return by reference is problematical. Okay? So what can go wrong? Look at these two declarations, M1 and M2. They are so close. M1, of course, is a copy of the result. No issue. M2, of course, is a reference, but what is it a reference to exactly? Good question. The arguments in these examples are, I'm pretty confident in saying they're temporaries. I mean, let's be honest, it could be macros for all I know, but let's say not. And those temporaries' lifetimes will expire at the end of the statement. So I'm left with a dangling reference to, either this corpse or that corpse. Corpse? Well, what else is it? Dead, gone, and buried. And we've recycled the grave, yes. Okay. Of course, we want to avoid that. I hope you agree. I found somebody who posted this quote. He says, I wonder why this hasn't been an error all along. Is there any legit, my underlining, any legit reason on some niche architecture why anyone would ever want to return a reference to a temporary? Yeah, I don't know who this is, but that's the handle. Yeah, I don't know. And there are more issues. Since min is returning by reference to const, callers can't do this, which, kind of seems reasonable if you have, for example, ints, numeric types. Whichever one is smaller, set it to 0. Can't do that. It's const, reference to const. Or, call some mutator if it's a class type. Can't do that. It's const. Now, people try to make it work nonetheless. So you try to const cast and throw away the constness, and that it just doesn't work. Okay. I mean, it's a temporary. It's dead and buried. Why are you trying to mutate it? And I've had this argument with, I can't tell you how many dozens, if not hundreds, of programmers. This is a significant problem. Found this last month. Somebody wrote, I recently got burned by a piece of innocent looking code that was something like this. See the temporary there? B minus A, that's a temporary. The problem stems from the fact that standard min-max returns a pair of tconst refs, regardless of what the arguments are, and he's begging for a fix. Okay? And no, I'm not going to tell you who posted that. I don't want to embarrass anybody. And if you're still not convinced, last month, swear to God, I wasn't looking for this, came across my desk. Here's the commit message fixing 2 issues in GCC's standard library. Here's the overview. Fix a dangling reference crash and of all places, is permutation. How long has that been in the standard? 20, 30 years? Yeah. The code was caching the result of this invoke in a local auto ref variable. The problem is that this may create dangling references. Lifetime extension, which sometimes applies but does not apply here because of the expressions involved. This tells me that it's pretty clear, to at least to me, I hope to you too, that even the most expert, and these people are among the most expert programmers I know, they occasionally run afoul of this imperfect return. And it's equally clear, at least to me, that some mitigation seems in order. So we're going to try to do better. Now, we have several goals in mind. Still want to avoid unnecessary copying. Certainly want to avoid dangling references. Want to avoid any need for const cast or anything, equally ugly. Of course, I want to preserve correct results. And if I have all four of those, this is what I've called the perfect return. Now, nothing I'm going to show you tonight, or have shown you, or will show you, is original, except the presentation itself. Okay? I don't claim to be the first to do this. Okay? Too many other C++ programmers in the world. And while we're at it, maybe we can consider cross-typing. Interestingly, there was a solution proposed nearly 20 years ago by Howard Hinnant. But back then, it took 175 or so lines of code, and the standards committee rejected it because of perceived complexity. But back then, we didn't have common type in the standard. I had invented common type back in the late 1990s, and Howard picked it up and finally got it into the standard. It took an embarrassingly long time to get it right. It's incredibly tricky. But it was rejected. And since then, many other people have attacked this. Some of the results were pretty good, others were pretty bad. I've experimented with all of them, and some of them I now want to explore with you, and here comes part 3. Okay. Little bit of analysis. What are the return type options? We're still looking at min. If neither argument is a temporary, that means both are L-value expressions, right? Safely return a reference, not temporaries. I can refer to them. But what kind? If both arguments are mutable, I can safely return by mutable LREF, namely tref. Otherwise, I have to return by immutable LREF, so tconstref. Okay, that takes care of the case of 2 L-value arguments, expressions as arguments. Okay. If either argument is a temporary, which means it's an R-value expression of some sort, I dare not return any kind of reference because of the possibility of dangling very quickly. Even if only one is a temporary, if that's the result, I'm still in trouble, right? So the only safe choice is to apply a copy or a move and return by value. It's the only safe thing to do. Which is kind of similar to what the ternary does, isn't it? Yeah. So I've got 3 viable return types, right? I can return a tref, which is safe when I've got 2 mutable L-value expressions. And now we no longer have to cast away constness. I can return a tconstref when I have at least one immutable L-value reference. And otherwise, I have to return a plain T, which is by value. And that's how I avoid dangling. Okay? So it looks like we need numerous overloads. Okay? This is going to seem a little bit strange, but you have to look at all of these as an overload set. You can't just look at any one of these in isolation, because we get the wrong impression, potentially. Okay? Here's the return by mutable LREF. That one's pretty straightforward. Here's the return by const LREF. So far, so good. Now, what do I do about the temporaries, the R values? Can't do it in one, because I might have one or the other or both. So I need 3 overloads for those cases. And this looks wrong because of the tref. Because that's a what? That's a forwarding reference, right? So it could deduce an L value reference. But the one up above is a better match. So overload resolution will do the right thing. Okay? That's what I meant when I said consider the whole thing. And just to complete it, every one of those overloads will have the identical body. Okay? And that's the same body we've seen all along. Okay? This is really not a good solution, though. Number one, it's ugly. And it certainly doesn't scale. What do I do when I have 3 arguments in some function or more? I mean, heaven forbid, but it happens, right? Let's try something else. We can make do with 2 overloads. Here's the L values case. And you need to write it like this. Don't try it with a template keyword. It gets very ugly very quickly. And notice there's a requires clause. I'll show it to you at the bottom of the screen. Okay. So there's case 1. Here's case 2. Otherwise, I have one or both arguments that are R value expressions. And now I have to do perfect forwarding to get the right answer. And then the purpose of the requires clause is to make sure that I have only same type expressions. So that's a little bit of ugly, but you know, C++. Well, that's a lot better, but can we do still better? Spoiler alert, yes. Okay. So if we want to do even better, I'm going to pick a different poster child just for simplicity, okay? Identity function. You hand me something, I hand it back to you. Identity. But I don't know a priori either the type or the value category of that one argument. So there are 3 questions to be asked and answered. How do we declare the parameter, the sole parameter? How are we going to declare the return type? And how do I write the operand of the return statement? Because the rest is mostly boilerplate. Okay? Let's answer those one at a time. How do we declare the parameter? Well, we know how to do this. We just use a forwarding reference. And we're kind of playing fill in the blank here. Okay? Decal type auto does exactly what we want. Sorry. Jumped ahead. tref does exactly what we want here. Capture the type and the value category. Okay. Return type. Well, I already gave it away. We got to preserve any reference qualifier, so decal type auto is the right tool for the job. Which is why I kind of beat on that for a while at the beginning. And now it gets interesting. How do I write the operand of the return? I need to return some expression such that if we were called with an L value expression, I return it by reference of some kind. And if we were called with an R value expression, I return it by value. And once I can do both of those, I will have the perfect return. Okay? There's the problem to be solved now. And we've got all the tools. But let's brainstorm a little bit. I mean, the obvious thing is just return T. That won't do it because that's always going to make a copy, and that's not necessary if it's an L value. I just want to return the reference. And if you have C++ 23, we've got this new thing called auto. okay, which is the language version of decay, what used to be called decay copy, if you remember that. Okay. What if I try to do perfect forwarding in the return? It's not the usual application for perfect forwarding, but try that. And I'm going to abbreviate this, with using the macro FWD from now on. Well, this will work for L values, but it's going to allow R values to dangle. So this doesn't do the job. I mean, for example, if the caller does something like this, immediate dangle. Remember, I want to return value by value so that there's no dangling for this case. And keep in mind, T is going to be deduced as a reference type when I started with an L value expression and a non-reference, yes, a non-reference when we started with an R value expression. This is not, I'm not talking about decal type of the parameter. I'm talking about T. The parameter is T ref ref. What's T? Okay. It's either an L value expression, L value reference type, or it's a non-reference type. Keep that in mind. Here we go. We're going to do a cast, or something that looks like a cast, an old style cast. Ta-da! This does exactly the right thing. It's one line of code. It's one line of code. If I was called with an L value expression, it's a cast from an L value reference to an L value reference, which is the no-op. If I started with an R value expression, then T is a non-ref, so I'm calling a constructor, do the cast. And I get a copy or a move if possible. And in either case, when copy elision applies, the result is actually constructed in the caller's space. So that actually will avoid any extra copy or move in most cases, actually. Okay. Okay. If you don't like using the old style cast notation, feel free to write it like that, which is a static cast followed by another static cast, because that's what the macro is. Okay. I consider that to be opaque and damn near cryptic.
C++.
It's C++. Yes, thank you. Your check will be in the mail. No, I'm sorry. Okay. Now let's go back to my first original poster child. Ta-da. Done. Done. Quick recap. I started with, and I picked argument A, but this applies to B just as well, okay? If I start with an L value expression, the decal type of that is going to be an LREF, and so the type is also going to be an LREF, and a forwarded LREF is also an LREF, so A of forward of A is an LREF, and that's an identity, and that's a no-op. Costs you 0. If you start with an R value expression, the decal type is an R value reference, so A is a non-ref type, and a forwarded non-ref is an R value reference. But when you apply the cast, you get a non-ref because you're calling a constructor. Okay, so it does the right thing. And then finally, the ternary does exactly the right thing if I have, one from column A, one from column B. Done. So how did we do? Well, remember I had 5 goals for improvement. No unnecessary copying, check. No dangling references, check. No need for const cast, check. Preserving correct results, check. Cross-typing, check. Cross-typing, did you catch that? Cross-typing. And move-only types, check. And along the way, I think we acquired a couple of deeper insights, culminating in 4 lines of code, of which one was interesting. And all of this is absolute standard C++ language and library. No invention. And so we have what I've called the perfect return. Initialize 1 or more parameters using forwarding references, apply whatever logic the algorithm calls for, and you're going to return one of those passed in values, and you forward it through what looks like a cast or a constructor, call it whatever you want. And then we prototype this in our 2 poster children. There's identity, just as a recap. And there's min as a recap. And with that, thank you. If you have the patience, I have the time. I'll be happy to take questions up to a point. I do have to get home tonight. Okay, so whoever's first, nice and loud. I'm an old man. Please.
Yeah, I guess I have a question. It's like, why? Why the compiler knows that, and it knows what the caller wants. Why even make it do anything? Why would you want anything else?
The compiler doesn't know what you want. The compiler never knows what you intend. It only knows what you wrote.
If you declare the type, right? If you declare you want a reference type and it knows it can't return reference type, it's an error. If you declare you don't want a reference type, then it's going to use copulation and whatever else it knows.
I don't want to do all that. That's more work for me. You've just outlined 2 possible return types. I don't want to do that. I do it in 1. I just say decal type auto.
But if I took that away, used your code, right, and declared a reference type, but then.
But that's the wrong result type.
Right, then I'm going to get an error anyway, right?
Not necessarily. Not necessarily. You're going to get a dangling reference. We talked about that.
And that's why would you even allow something? What would be?
Because the compiler doesn't know your intention. It doesn't know that you're going to try and bind this to a reference at the far end. You're looking at a function. It doesn't know what you're going to do with the result. Maybe you're going to copy it, in which case it's safe. You don't know what the result is. Okay? Remember separate compilation. I don't know what you're going to do with my result, and it's none of my business. Nope. Template code is not special. Template code is just code. It is not special. No joke. Templates are not special. They're different. They have their own set of rules, additional rules, I should say, but they're not special. Programming with templates is just programming. If you don't believe me, come take my 2-day seminar. All about templates. Trust me, in 2 days. Yes, sir.
How it collapses when we have two references. How they you see that they collapse. Can you explain how it happens in low level
In the binary level? No, because that doesn't exist. Okay. Reference types don't have, an entity of a reference type does not have to occupy any storage. It might, or it might not. That's up to your implementation. So no, can't tell you. Sorry. Sorry, can't hear you.
take care of it beforehand, I guess.
The compiler does the right thing.
But yeah, that's why you're saying it doesn't exist at the binary, it doesn't exist at the machine level, right? Because it's like, kind of like map, map goals where it's always just done beforehand. That's why.
Modern compilers are astonishingly good. If you don't believe me, go dig up a talk given by this gentleman, our friend Matt Godbold, the sometime verb. Modern day compilers are astonishingly good. They're not bug-free, but they're damn good. It's been a long time since I found a compiler bug. Sir, and then I'll come back to you.
Is there any practical application of constant R-value references?
Constant R-value references, not much, no. But there was no reason to disallow them. Right? I don't know if I've ever written an overload that takes a const R-value reference. Sorry, R-value reference to const. Yeah. I can't remember one offhand.
The only application for them is to delete this function, but I still cannot figure out how it helps.
Well, I mean, some things can bind to it, but whether that's something you want, yeah, I can't answer that. It's up to your application. All right, back to you, sir.
We have the same-
And I'll get you next.
we have the same question. So what makes two references to collapse?
Oh, because what makes two references collapse? I showed the example. Start with one. So suppose I have R as an alias for int ref. And now somewhere else in the program, I write R ref. But R is already a synonym for int ref. So I have int ref to which I want to apply a ref. That looks like a reference to a reference, but there's no such thing. So they collapse. Got it? Good. You're welcome. Yeah. Sorry.
I guess I know your answer, but.
You know my answer. This is a telepathic gentleman in the front row.
No. I was gonna say that I didn't know a lot of this stuff, so I was doing something that apparently is not very good, but I'm just gonna tell you, for things like mean or compare, say you have a new type and you wanna define a comparison operator for that. If my inputs are something like integers, it's just better to put less than operator int x, int y, instead of int const reference x, int const reference y, say. But if I have like some types that are really large and I don't want to copy them.
You're talking about parameter passage.
Yeah.
Declaring parameter types. Yeah, I understand.
So I used concepts to say const reference of t type. And if my type is like small and it is contiguous, and
Yeah.
I would just say that means its value. If my type is not something small and contiguous, I would then that is.
Yeah, we all have to make decisions about how we declare our parameter types. Sure. And I've played with things along the same line,
What is now your criticism of doing that instead of this?
It's not an extent of. They have nothing to do with each other. Okay. The discussion was not about parameter passage and not really about comparisons either. Comparisons are actually pretty badly handled in most programs. Okay. And I don't know why anybody wants to write an operator less than or greater than anymore. Just, write spaceship, be done with it. And maybe augmented with an equality operator. If you want to do short circuiting at something, right? You want to do spaceship on vectors, for example. Well, if they have different sizes, they're not equal, right? So write your own equality operator that, does the fast thing and let spaceship do the rest. That's my friendly advice for the day, and now I'm getting off my soapbox. All right, somebody else? I thought I saw, yes, ma'am.
So remembering to do like the to cast the forwarded parameter.
Yes.
Kind of two steps. I was thinking if your implementation of identity, if you pass T explicitly, could that be an encapsulation of the perfect return as the function?
Could that be an encapsulation? Sure, it could, but I don't believe in magic wands. Spoken by a guy who used to make his living as a stage magician. How do you think I could afford graduate school? No joke. In general, I recommend never passing a template argument explicitly. Now, there are cases you can't avoid it, but type deduction generally does the right thing that you want. Okay. Now, having said that, I've seen people call standard min of their type. It's generally a practice to be discouraged. Okay. And the reason for that is very pragmatic. You're making an assumption about how the standard library works. The standard specifies, it does not implement. The implementation doesn't have to look anything like what the standard specifies. It just has to do the right thing by the right name. If you ever get a peek at my standard library, you wouldn't recognize it because I don't have to support customers, so I can do whatever I want. But more interestingly, I very rarely write function templates anymore, except as members. All of my algorithms are structs. Every damn one. Whether you call sort or exchange or swap or iter swap or any of them, they are structs that have an operator apply or operator parents, call operator. Okay. And that keeps me out of ADL hell. And if I want ADL, I can do it from inside my struct. Okay? And if you want to know how to do that, send me an email. I'll give you some references. It's not hard. It's a minor nuisance, but it's a minor nuisance. Okay? It involves things like they've named it poisoning a declaration. Yeah. Define a function as deleted for a positive result. It enables ADL because it'll find it. And since it's a function, it says, okay, this one isn't a good candidate, but now I can go look elsewhere. All right? I am a fan of ADL. I don't have a problem with ADL, but I know how to write my algorithms. Anybody else? Going well? Oh, sir.
I noticed that when you said int x equals 42, you said, well, let's give it an additional value. I don't care what it is. But you must know that 42 is the most important number in the universe.
Well, no, but okay. I know that some people believe 42 is the most important number in the universe. I have other numbers that are far more important. 0 comes to mind. Sir.
I was just interested in the FWD macro that you showed.
Yes.
I can't see how you could implement that as written. Can you explain how FWD works? And my argument for that is,
Oh, sure.
When you have stood forward, you have to refer to the T. Go on.
You don't. Decal type is your friend.
So
I don't know if everybody heard the question. He's talking about the FWD macro that I was applying. Okay. Decal type is your friend. Pound define FWD of X as static cast to decal type of X in angle brackets. I think no, you don't need, no, you don't need the ref again,
Yeah.
of X.
Just another parameter for the T.
No, you don't need it.
That's why I was.
The application can deduce it. The use cases for forward, the only cases I've ever seen for forward are when you want to forward a parameter. And when you forward the parameter, you can say decal type of that parameter. And it'll give you most of what you want. Okay, you're welcome. If anybody needs more details, send me an email and I'll send you a one-line reply. It starts with hint, it starts with pound define. Sir.
I think you had some questions on the Zoom.
Oh, I don't have access to Zoom here.
See any questions on Discord?
Someone had their hand.
I
Well,
don't.
they have no ability to.
They-
ask
they-
questions
you can't-
anyway, so We're watching the Discord and Slack.
Yeah, if they have a question, we're gonna have to ask about Discord.
Okay, so we have no questions on Zoom despite serious attempts.
Sorry.
No? Yeah. Oh, sorry about that if you're on Zoom. Yeah, not my doing. Sir.
That use the already 9 different overloads, right?
5, but
Okay,
small value of 9. Yes, I understand.
against your final perfect implementation. My question is, certainly we can agree that it's more elegant to collapse it down into the 4 lines that you ended up with. The question is a matter of performance or compiler output, this sort of thing. Can we also assume that it would be more compact, or is that variant on the compiler?
What you can assume is it takes fewer resources from the compiler. If I have 5 templates to be considered, that's 5 instantiations or potential instantiations, 4 of which get discarded, etc. That's work. Okay, it's not free. 1 template, 1 instantiation, you're done. And don't forget, I threw in cross-typing for free. I'm not convinced that cross-typing is a good idea, but the ternary will do the right thing. And I don't know if you noticed, but the min was constrained so that the comparison operator would work. Okay. Yeah, I didn't make an issue of pointing it out, but okay. I'm hoping that, my kind of beating on the language for the better part of an hour paid off in the end, because that's what I was going for. Okay. So I hope everybody gets to take away at least a little something. I'm sorry, I'm not sure who was first. Yeah, please.
You mentioned whenever 2 R value refs were the results of a ternary operator, that's a valid case. Is that correct? And
If you hand the ternary operator a pair of the right kinds of expressions, yes, you can get an R value reference out of the result.
Is that handled by, I don't remember seeing it in the 5 cases. No, okay.
Oh, yeah, it is handled.
Okay.
It is,
You can have-
it is handled implicitly rather than explicitly. Remember I said
Yeah.
there's a forwarding reference in several places,
Yeah.
and it looks like that's going to do the wrong thing, but there's a better match up above that takes care of the wrong thing. So that's,
Still return an R value reference?
no.
Okay,
Well, it's not supposed to,
right.
because that's when we need the copy or move.
Yes, that sounded like
Yeah,
crazy to me.
yeah, yeah. It's interesting. I get to argue with a lot of programmers about X value expressions. But an X value expression, you can't get one by accident. You pretty much always have to say move of something. Okay. I mean, that's not the only way, but it's by far the most prevalent, right? So it's not an accident that you have one of those. And what you're saying is, yeah, I know you're technically an X value, but please, please, please treat this as if it were a PR value. It's an explicit request. I don't care that it's an L value, treat it as if it's a PR value. And we happen to name that X value. Okay. So at the far end of things, you can just talk about L values and R values. And R value subsumes those two cases. Okay. And, you know, I sometimes get a little sloppy about that, but that's the reasoning. Okay. Yes, sir.
Ternary operator and the cross typing isn't subject to like type slicing. And that the caller, especially if you're using auto, isn't going to be aware of.
Is there the potential for slicing? I have not thought deeply about this. Probably, but also probably not very often. There's a lot more to the, please. There is so much more to the ternary operator that we have not discussed. Okay. So much more. Okay. Because C++ has some bizarre rules. Okay. What if one of the operands has type void? That's legal. For example, put a throw expression in there. For purposes of the ternary, that has type void. Right? The ternary operator is a page and a half of pretty fine print in the standard. Slightly more than a page and a half, I think. I actually have a quote back here somewhere. Let me see if I can find it. Nah, I went back too far. Here are some of the things I did not talk about today. Bit fields, enums, throw expressions, array types, pointer and member types, no putter type. What do you do when you have indeterminate values or erroneous values? Here's the quote by our good friend Barry. He's right. It is. He's right. Okay. Getting late, people. Anybody have a wrap up? No? Going once, one more. Hold your applause. Sir.
Is the type of a throw void, or is the type of throw no return, or no return out of types?
There's no such thing as no return. For purposes of the ternary, the type of a throw expression is void. Okay. And I've used that very successfully when trying to initialize a member of a class, and I have to check for something that, you know, isn't right, and, you know, doing a ternary. Here's the thing I really want, but if it's not valid, throw, you know. And you do it in the ternary expression and it works beautifully. Ternary expression is an incredibly useful and powerful tool. I don't know why so many C++ programmers have an innate dislike or distrust or hatred. Yeah, okay, fine. All right. Say goodnight, Gracie. Thank you, everybody. Always a pleasure to talk to the home